Imagine holding a grain of sand in the palm of your hand. It feels solid, unmoving, permanent. Now imagine zooming in. First, you see tiny crystals. Zoom further, and those crystals become molecules. Closer still, and the molecules dissolve into atoms. Continue your journey, and the atom itself appears almost empty, with electrons surrounding a tiny nucleus. For more than a century, this seemed like the end of the story. The universe, we believed, was built from particles, tiny, indivisible objects that simply existed as the fundamental ingredients of reality. But then, physics quietly overturned that picture. According to the most successful scientific theory ever developed, those particles are not truly fundamental at all. An electron is not actually a tiny ball traveling through space. A photon is not simply a little packet of light flying across the universe. Even the quarks inside every proton and neutron may not be permanent objects in the way our intuition imagines. Instead, modern physics suggests something far stranger. The entire universe is filled with invisible fields. They exist everywhere, even in places where we would normally say there is absolutely nothing. Empty space is not empty. It is alive with these fields. Every electron you've ever seen is merely a tiny vibration of one invisible field. Every photon is a ripple in another. Every quark, every neutrino, every force carrier emerges from its own field, stretching across the entire observable universe. If every particle is merely a ripple, then what is actually doing the rippling? And perhaps the deepest question of all, why does nature choose quantum fields instead of particles in the first place? Physics can describe these fields with astonishing precision. The equations predict experimental results accurate to more than 10 decimal places. They explain lasers, semiconductors, nuclear reactions, black holes, and even the earliest moments after the Big Bang. Yet nowhere do the equations explain why reality itself should be built from fields. That mystery remains one of the deepest unanswered questions in all of science. Tonight, we're going to follow this mystery from the familiar world around us all the way to the edge of modern physics. Along the way, we'll encounter galaxies, black holes, quantum fluctuations, the birth of the universe, invisible oceans of energy, and ideas that challenge our most basic intuition about existence itself. Because by the end of this journey, you may never think of empty space the same way again. For thousands of years, humanity believed that every object could eventually be broken into smaller pieces until an indivisible building block remained. Ancient Greek philosophers even gave this hypothetical building block a name, atomos, meaning uncuttable. It was an elegant idea. Everything, from mountains to rivers, from stars to living organisms, would simply be different combinations of tiny, eternal particles. For nearly 2,000 years, this remained philosophy rather than science. Only in the 19th century did careful experiments begin transforming these ancient ideas into measurable reality. Chemists like John Dalton noticed that elements always combined in fixed proportions. Water was always 2 parts hydrogen and 1 part oxygen. Carbon dioxide always contained 1 carbon for every 2 oxygen atoms. These simple numerical relationships hinted that matter might indeed consist of discrete units. As experimental techniques improved, evidence accumulated rapidly. Then, in 1897, J.J. Thomson performed an experiment that forever changed physics. By studying mysterious glowing beams inside vacuum tubes, Thomson discovered something smaller than atoms themselves, the electron. The supposedly indivisible atom was suddenly divisible. It was a revolutionary shock. Soon afterward, Rutherford fired alpha particles towards thin sheets of gold foil. Most passed straight through, but a tiny fraction bounced backward almost as if they had struck something incredibly dense. Rutherford famously remarked that it was as astonishing as firing a cannonball at tissue paper and watching it bounce back. His experiment revealed that atoms are mostly empty space surrounding an incredibly tiny nucleus. By the early 20th century, the picture seemed straightforward. Matter consisted of electrons orbiting nuclei. The nuclei contained protons. Later, neutrons would also be discovered. 3 particles appeared sufficient to explain nearly everything around us. For a brief moment, physicists believed they were approaching the end of their quest. Nature seemed understandable. Everything appeared to be made from little objects moving through otherwise empty space. If you had asked a physicist around 1910 what reality fundamentally consisted of, many would probably have answered with confidence, tiny particles, nothing more. But reality had already begun preparing another surprise. Around the same time that atoms were being understood, another mystery emerged from an entirely different direction: light. Isaac Newton believed light consisted of particles. Christian Huygens argued it behaved like waves. Throughout the 19th century, experiments overwhelmingly favored the wave picture. Thomas Young's famous double-slit experiment demonstrated interference patterns that only waves seemed capable of producing. James Clerk Maxwell then unified electricity and magnetism into a single, elegant theory. His equations predicted electromagnetic waves traveling at exactly the measured speed of light. Light appeared to be a wave moving through space. Problem solved. Except it wasn't. In 1900, Max Planck was studying heated objects. Whenever something becomes hot, it glows. A fireplace emits red light. Molten iron glows orange. The surface of the sun shines brilliantly white. Physicists wanted to predict precisely how much energy these objects should radiate. Classical physics completely failed. The equations predicted something absurd. As frequency increased toward ultraviolet light, the emitted energy should increase without limit. This impossible prediction became known as the ultraviolet catastrophe. Nature clearly refused to behave this way. Planck desperately searched for a mathematical solution. Eventually, almost reluctantly, he proposed something extraordinary. Perhaps light energy could only be emitted in tiny discrete packets, not continuously, not smoothly, but in indivisible chunks. Planck considered this merely a mathematical trick. Even he doubted that nature actually worked this way. Yet his equations perfectly matched experimental observations. 5 years later, Albert Einstein took Planck's strange idea seriously. He argued that light itself consisted of tiny packets of energy. Today, we call them photons. Suddenly, light behaved like both a wave and a particle. Neither description alone was sufficient. Reality had become stranger than anyone expected. Then came Niels Bohr. Electrons orbiting nuclei should continuously radiate energy according to Maxwell's equations, gradually spiraling into the nucleus. Atoms should collapse almost instantly. Yet atoms clearly remained stable. Bohr proposed another radical idea. Electrons could occupy only specific energy levels. They could jump between these levels, but never exist in between. Again, nature refused to follow common sense. By the mid-1920s, the situation had become deeply confusing. Light behaved like waves, then like particles. Electrons behaved like particles, then like waves. Every experiment seemed to contradict another. The old picture of tiny solid objects traveling through empty space was beginning to crumble. Then came one of the astonishing discoveries in scientific history. In 1924, a young French physicist named Louis de Broglie suggested something that sounded almost ridiculous. If waves can sometimes behave like particles, perhaps particles can behave like waves. Not merely resemble waves, actually possess wave-like properties. His idea seemed almost impossible to believe. After all, we never observe baseballs producing interference patterns. Cars don't diffract around buildings. People don't spread out like ocean waves. Yet de Broglie realized something remarkable.
The wavelength associated with ordinary objects is unimaginably tiny because their masses are enormous compared with individual electrons. The wave nature is still present. It simply becomes far too small to observe. For electrons, however, those wavelengths become experimentally measurable. Only a few years later, experiments by Clinton Davison and Lester Gearmer confirmed de Broglie's prediction. Electrons produced interference patterns exactly like light waves. Particles were behaving as waves. This discovery shattered the remaining certainty surrounding classical particles. If electrons could interfere with themselves, what exactly was an electron? Was it a tiny object? A wave? Both? Neither? Even today, nearly a century later, physicists still debate how best to interpret this strange behavior. Erwin Schrödinger attempted to answer this mystery mathematically. Instead of imagining electrons as little planets orbiting atomic nuclei, he developed an equation describing wave functions. The Schrödinger equation became one of the most successful equations ever written. It predicted atomic behavior with astonishing accuracy. Yet it introduced another mystery. The wave function did not describe a physical wave moving through ordinary space like ripples across water. Instead, it described probabilities. Before measurement, an electron seemed to exist in many possible states simultaneously. Only when observed did one definite outcome emerge. This was no longer simply strange physics. It challenged humanity's understanding of reality itself. Werner Heisenberg deepened the mystery further with his uncertainty principle. The universe itself imposes limits on what can simultaneously be known. The more precisely position is determined, the less precisely momentum can be known. This limitation is not caused by poor instruments. It is woven into the fabric of nature. Reality itself appears fundamentally uncertain. The universe, once imagined as an enormous cosmic clock operating with perfect predictability, suddenly became governed by probabilities. Einstein disliked this conclusion. His famous remark, "God does not play dice," expressed his discomfort with quantum mechanics. Niels Bohr famously replied that perhaps it was not humanity's place to tell nature how it should behave. The debate continues today. Yet, despite philosophical disagreements, quantum mechanics proved astonishingly successful. Every experiment confirmed its predictions. Every technological revolution of the 20th century, from transistors to lasers to magnetic resonance imaging, rests upon these quantum principles. Still, something enormous remained missing. Quantum mechanics explained matter beautifully, but it did not fully explain the forces acting between particles. Gravity was described by Einstein's general relativity. Electromagnetism followed Maxwell's equations. The quantum world and the relativistic universe remained mathematically incompatible. Physicists needed a deeper framework. And it was during that search that an extraordinary realization slowly emerged. Perhaps the problem was not with the equations. Perhaps the problem was our picture of particles themselves. Perhaps particles had never been fundamental at all. Perhaps something even deeper filled every corner of the universe, silently giving birth to everything we had ever called a particle. For decades, physicists had been trying to force two completely different pictures of nature to coexist. On one side stood Einstein's universe. Space and time were not separate things, but parts of a single four-dimensional fabric called spacetime. Gravity was no longer a mysterious force pulling objects together across empty space. Massive objects simply curved space-time itself, and planets, stars, and even galaxies followed those curves as naturally as a marble rolling across a stretched sheet. On the other side stood quantum mechanics.
Here, particles behaved like waves, probabilities replaced certainty, and even empty space refused to remain truly empty. Both theories worked astonishingly well. General relativity predicted the bending of light by gravity, the expansion of the universe, black holes, gravitational waves, and the precise orbit of Mercury. Every major experimental test has confirmed Einstein's equations with extraordinary accuracy. Quantum mechanics was even more successful. Its predictions were so precise that some experiments agreed with theory to more than 1 part in a trillion. Modern electronics, computers, lasers, GPS satellites, and nearly every advanced technology surrounding us today depend upon quantum theory being correct. Yet there was a problem. These two magnificent theories seemed to speak completely different languages. General relativity described smooth, continuous geometry. Quantum mechanics described discrete probabilities. Trying to combine them often produced infinities that made no physical sense. The deeper physicists looked, the more it seemed that nature was trying to reveal an entirely different picture. The breakthrough began almost quietly. It did not arrive through a single spectacular experiment, but through decades of mathematical discoveries made by physicists attempting to solve practical problems. One of those physicists was Paul Dirac. Dirac possessed an extraordinary gift for seeing mathematical beauty where others saw only complicated equations. In 1928, he developed an equation that successfully combined quantum mechanics with Einstein's special relativity. The equation described electrons moving at speeds approaching that of light. It worked beautifully, but something strange emerged from the mathematics. The equation predicted solutions that nobody expected. Particles identical to electrons but carrying positive electric charge. At first, many physicists believed these solutions were mathematical nonsense. Nature surely would not contain such bizarre mirror particles. Yet only 4 years later, Carl Anderson discovered exactly such a particle while studying cosmic rays. It became known as the positron, the first confirmed antimatter particle. Mathematics had predicted an entirely new form of matter before anyone had ever seen it. This was one of the greatest triumphs in theoretical physics, but it also hinted at something profound. Perhaps equations were revealing aspects of reality far beyond ordinary intuition. As more particles were discovered during the following decades, physicists found themselves facing an unexpected crisis. Instead of 3 fundamental particles, laboratories began uncovering dozens. Muons, pions, kaons, lambda particles, sigma particles, xi particles. Eventually, hundreds of seemingly fundamental particles appeared. The situation became almost embarrassing. Enrico Fermi once joked that if he could remember the names of all these particles, he would have become a botanist instead. Particle accelerators were revealing what newspapers began calling a particle zoo. Every increase in collision energy seemed to produce entirely new particles. Had nature suddenly become infinitely complicated? Or was there a deeper pattern hidden beneath the apparent chaos? The answer began emerging during the middle of the 20th century. Many of these particles were not truly fundamental. They resembled atoms in an unexpected way. Just as atoms are built from electrons surrounding nuclei, many newly discovered particles were themselves combinations of even smaller ingredients. Eventually, Murray Gell-Mann and George Zweig independently proposed the existence of quarks. Protons and neutrons, once considered elementary, were actually composed of smaller constituents. Today, we know that an ordinary proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. This discovery dramatically simplified the growing particle zoo. But it also raised another question. If protons are built from quarks, what are quarks built from? Despite decades of increasingly powerful experiments, quarks themselves continue to behave as fundamental objects. No internal structure has ever been observed. Yet even this statement requires careful wording. Modern physics no longer says quarks are little balls. It says something far stranger. To understand why, we need to forget almost everything everyday experience teaches us about objects. Imagine standing beside a perfectly calm lake just before sunrise. The water appears completely still. Then someone drops a pebble into its center. Circular ripples spread outward across the surface. Now imagine someone asks a simple question: what is moving? Your first instinct might be to answer, the ripple. But think carefully. The ripple itself is not an object. No individual piece of water travels across the lake from the center to the shore. Each individual water molecule merely moves up and down by a tiny amount. The ripple is not a thing. It is a pattern, a disturbance, a traveling excitation of the water itself. This simple observation turns out to be astonishingly important, because modern physics suggests that electrons behave much more like ripples than tiny marbles. Only the water beneath those ripples is invisible. That invisible water is what physicists call a quantum field. This word field is one of the most misunderstood terms in science. When many people hear it, they imagine something spread through space like a fog or perhaps an invisible gas. But that picture is misleading. A field is not made of tiny particles. Instead, it is a physical quantity assigned to every location in space and time. This idea actually predates quantum mechanics.
Michael Faraday first introduced the concept while studying electricity and magnetism. Before Faraday, physicists imagined forces acting mysteriously across empty space. If the sun pulls on Earth through gravity, how does that pull travel across 150 million kilometers of emptiness? How does one magnet influence another without touching it? Faraday proposed a radical alternative. Space itself possesses physical properties. Place a charged object somewhere, and the surrounding space changes. Place a magnet nearby, and space changes again. Instead of objects reaching across emptiness, the space between them becomes an active participant. James Clerk Maxwell transformed Faraday's intuitive ideas into mathematics. His equations revealed that electric and magnetic fields were not separate phenomena. They were different aspects of one unified electromagnetic field. Even more astonishingly, disturbances in this field travel through space at a fixed speed. When Maxwell calculated that speed using laboratory measurements of electricity and magnetism, he obtained approximately 300,000 kilometers per second, exactly the measured speed of light. Light itself turned out not to be separate from electromagnetism. Light is simply a wave traveling through the electromagnetic field. That realization completely transformed physics. Yet Maxwell still imagined continuous classical fields. Quantum mechanics would eventually make those fields stranger than anyone expected. By the 1930s, physicists were asking an unavoidable question. If light is a quantum object, shouldn't the electromagnetic field itself also obey quantum mechanics? The answer led to one of the greatest revolutions in scientific history. Instead of imagining photons as tiny bullets flying independently through empty space, physicists discovered something fundamentally different. There is only one electromagnetic field filling the entire observable universe. A photon is merely one quantum of excitation within that field. In other words, the field exists first, the particle appears second. This sounds like a subtle distinction. It is not. It changes everything. Imagine an ocean stretching endlessly in all directions. When no wind blows, the surface appears calm. As wind begins blowing, waves emerge. Would it make sense to say that the waves exist independently of the ocean? Of course not. The waves are simply temporary motions of something deeper. Likewise, modern physics does not treat photons as independent little objects. They are temporary excitations of an underlying electromagnetic field. Exactly the same logic applies to electrons. There exists one electron field permeating the entire universe, not one field per electron, one single electron field. Every electron ever created, from those inside your body to electrons orbiting distant galaxies billions of light years away, all originate from one single field extending across all of spacetime. They are not independent creations. They're different vibrations of the same underlying reality. This idea becomes even more remarkable when we consider one of the oldest mysteries in physics. Why are all electrons perfectly identical?
Imagine manufacturing billions of tiny steel balls. Even with extraordinary engineering, each ball would differ slightly. Some would be microscopically heavier, others slightly larger. No manufacturing process produces absolute perfection. Yet nature does exactly that. Every electron ever observed possesses exactly the same mass, exactly the same electric charge, exactly the same spin, exactly the same magnetic properties. No exceptions have ever been found. This puzzled physicists for generations.
Quantum field theory provides an elegant explanation. Electrons are identical for the same reason every ripple on a calm pond follows identical physical laws. They all emerge from the same underlying medium. There is only one electron field. Every electron is simply another quantum of excitation within that field. Nature is not manufacturing separate electrons. Nature is exciting the same field repeatedly. This realization solved one mystery while creating an even deeper one. If particles are merely excitations, what determines which fields exist? Why one electron field? Why one photon field? Why 6 quark fields? Why neutrino fields? Why does the universe possess precisely these fields and not countless others? No accepted theory currently answers those questions. Instead, the Standard Model begins by assuming these fields exist. It then describes their interactions with astonishing precision. In other words, modern physics can explain how quantum fields behave, but it still cannot explain why reality contains those particular fields in the first place. And as physicists push this framework further, they uncovered something even more astonishing. They discovered that even the emptiest region of intergalactic space, far beyond the stars, beyond galaxies, beyond clusters of galaxies where almost no matter exists at all, is not truly empty. Something is always there. Something that can never be removed. Something that never completely rests. The vacuum itself is alive. There was once a simple idea that seemed impossible to argue against. If you remove every atom from a box, then the box is empty. Remove the air, remove every molecule, remove every speck of dust, shield it from light, cool it to temperatures only a tiny fraction above absolute zero. Surely at that point, nothing remains. For centuries, this was exactly how physicists imagined a vacuum. A vacuum was simply the absence of everything. No matter, no radiation, no particles, no activity, just empty space. Even Isaac Newton imagined space as an enormous stage upon which the universe performed its motions. Space itself did nothing. It simply existed, providing a silent backdrop for planets, stars, and light to move through. But the rise of quantum mechanics completely transformed this ancient picture. According to quantum field theory, the vacuum is not the absence of reality. It is reality in its lowest possible energy state. That sounds like a subtle difference. In truth, it changes everything. Imagine an enormous piano stretching beyond every horizon. It has no beginning and no end. Every key represents one possible vibration of a universal field. Now imagine that nobody is playing the piano. Does the instrument cease to exist? Of course not. The piano remains. It simply rests in its quietest possible state. Quantum fields behave in a surprisingly similar way. Even when no electrons are present, the electron field still exists. Even when no photons are traveling through space, the electromagnetic field continues to exist. Even if every particle could somehow disappear from the observable universe, the underlying fields would remain. The universe can never become fieldless. Particles are optional. Fields are not. This idea is one of the greatest conceptual shifts in the history of science. It means that when astronomers observe enormous regions between galaxies that appear almost completely empty, they are not actually looking at nothing. Those vast cosmic voids, some stretching hundreds of millions of light years, are still completely filled with quantum fields.
To appreciate just how empty these regions are, consider the Boötes void, one of the largest known cosmic voids. It spans roughly 330 million light-years. If the Milky Way were placed inside it, our nearest comparable galaxy would lie unimaginably far away. Entire regions of this immense volume contain almost no galaxies at all. To human intuition, such places seem like perfect emptiness. Quantum field theory says otherwise. Every cubic centimeter inside that enormous void contains exactly the same electron field that exists inside your body, exactly the same electromagnetic field, exactly the same Higgs field, exactly the same quark fields, exactly the same neutrino fields. The fields do not become weaker simply because matter is absent. They permeate all space-time equally.
This realization leads naturally to another extraordinary question. If the fields are always there, why don't we constantly notice them? The answer lies in one of the strangest principles of quantum mechanics. Nothing can ever become perfectly motionless. At first glance, this sounds absurd. Suppose you cool an object lower and lower, its atoms move more slowly. Lower the temperature further, the vibrations decrease again. Continue approaching absolute zero, minus 273.15 degrees Celsius. Classically, we would expect every atom eventually to stop moving altogether. Yet quantum mechanics forbids this. Werner Heisenberg's uncertainty principle does far more than limit measurement. It places a fundamental restriction on nature itself. A system cannot possess perfectly defined position and perfectly defined momentum simultaneously. If every particle inside an atom were forced into complete stillness, both its position and momentum would become exactly known. Quantum mechanics does not allow this. Instead, every quantum system retains a tiny, irreducible motion called zero-point energy. This is not energy supplied from outside. It is energy that cannot be removed. Nature refuses complete stillness. The same principle applies to quantum fields. Even in their lowest energy state, they cannot become perfectly quiet. Tiny fluctuations always remain. For decades, physicists wondered whether these fluctuations represented genuine physical reality or merely mathematical artifacts. Then, experiments answered. One remarkable example is the Casimir effect, predicted in 1948 by Hundred Casimir, a Dutch physicist. Imagine placing two perfectly conducting metal plates extremely close together inside a vacuum. Classically, nothing should happen. There's no air pressure, no electromagnetic radiation, nothing pushes on either plate. Yet experiments reveal something astonishing. The plates slowly move toward one another. No hidden magnets, no invisible gas. Instead, quantum fluctuations inside the quantum fields differ slightly from those outside them. This tiny imbalance produces a measurable force. The vacuum itself pushes. What had once been called empty space was now exerting physical pressure. The vacuum had become something measurable, something real. Today, the Casimir effect has been confirmed repeatedly with increasing experimental precision. It stands as one of the clearest demonstrations that quantum fields possess physical properties even when no particles are present. Yet, this is only the beginning, because fluctuations inside quantum fields can become even stranger. Richard Feynman often described quantum mechanics in ways that challenged everyday imagination. According to quantum field theory, interactions between particles do not occur because little objects throw forces at one another. Instead, the underlying fields interact. When two electrons repel each other, the process can be described mathematically as the exchange of photons. But these are not ordinary photons, like those reaching your eyes from a distant star. They are called virtual particles.
The name is unfortunate because it often creates misunderstandings. Virtual particles are not tiny, invisible balls popping into existence and flying around like miniature bullets. Rather, they are temporary disturbances appearing naturally within the mathematical framework describing interacting quantum fields. They cannot be directly observed in isolation. They do not violate conservation laws. Instead, they represent intermediate states within quantum interactions. Despite being unobservable individually, their collective effects are measurable with extraordinary precision. This distinction is important because popular science sometimes describes the vacuum as continuously creating and destroying particles from nothing. While that image captures part of the intuition, professional physicists use more careful language. The experimentally verified reality is that quantum fields fluctuate. Those fluctuations contribute observable effects, including shifts in atomic energy levels, corrections to particle properties, and measurable forces like the Casimir effect. Richard Feynman transformed these incredibly complicated calculations into elegant visual tools now known as Feynman diagrams. At first glance, they resemble simple sketches, straight lines, wavy lines, points where they meet. Yet behind these deceptively simple drawings lies some of the most successful mathematics ever developed. Imagine two electrons approaching each other. Instead of picturing tiny spheres colliding, Feynman described the interaction through the electron field and the electromagnetic field. The electrons exchange momentum through the electromagnetic field. The diagram summarizes an unimaginably complex quantum calculation into a picture that physicists around the world immediately understand. Every line represents not merely a particle, but an excitation of its underlying field. This shift in thinking changed particle physics forever. By the late 1940s, however, another crisis appeared. The calculations themselves produced impossible answers. Again. Whenever physicists attempted increasingly precise calculations, infinities began appearing everywhere. The predicted mass of the electron became infinite. Its electric charge became infinite. Its self-energy became infinite. Infinite quantities are usually signs that something has gone terribly wrong. For several years, many feared that quantum field theory might collapse entirely. Then came one of the greatest mathematical breakthroughs of the 20th century. Julian Schwerner, Shinichiro Tomonaga, Richard Feynman, later refined by Freeman Dyson. Together, they developed the modern framework of renormalization. The word sounds technical and uninspiring. Its consequences were revolutionary. Instead of treating the infinities as fatal, renormalization carefully separated physically measurable quantities from mathematical artifacts arising during intermediate calculations. The result was astonishing. Quantum electrodynamics, usually abbreviated as QED, began producing predictions of unprecedented accuracy. Perhaps the most famous example involves the electron's magnetic moment. Theoretical calculations and laboratory measurements agree to better than 1 part in a trillion. To appreciate how extraordinary this is, imagine measuring the distance from New York to Los Angeles with an error smaller than the thickness of a human hair. That level of agreement is almost unimaginable. No scientific theory in history has ever achieved greater experimental precision. This extraordinary success convinced physicists that quantum fields were not merely convenient mathematics, they reflected something profoundly real about nature. But as the theory grew stronger, the universe itself began looking stranger. Because quantum fields do not merely explain electrons and photons, they explain stars, they explain galaxies, they explain why chemistry became possible. They explain why your body exists. Travel backward in time nearly 13.8 billion years, not to the beginning itself, that remains beyond current physics, but to a tiny fraction of a second after the Big Bang. The universe was unimaginably hot. Temperatures exceeded trillions of degrees. No atoms could survive, no nuclei, no molecules, not even protons or neutrons remained intact. Instead, the cosmos existed as an extraordinarily dense plasma of quantum fields interacting. The familiar particles of today constantly appeared, disappeared, collided, and transformed into one another. Energy flowed continuously between the fields. The distinction between matter and radiation became almost meaningless. The universe behaved less like a collection of objects and more like a restless ocean whose waves continually merged, split apart, and reformed. As expansion continued, the temperature gradually fell. This cooling changed everything. Quantum fields that had once fluctuated violently began settling into lower energy configurations. Quarks became permanently confined inside protons and neutrons through the strong nuclear force described by quantum chromodynamics, or QCD. A few minutes later, nuclei formed. Nearly 380,000 years after the Big Bang, electrons finally combined with those nuclei to produce neutral atoms. Only then could light travel freely across the universe. That ancient light still fills the cosmos today. Astronomers call it the cosmic microwave background. It is not merely old light, it is a snapshot of quantum fields cooling into the stable universe we now inhabit. When satellites such as COBE, WAMAP, and later the Planck spacecraft mapped this radiation with extraordinary precision, they found something remarkable. The early universe was almost perfectly smooth, but not completely.
Tiny fluctuations existed. Their differences amounted to only about 1 part in 100,000. Those minuscule variations eventually became everything. Over billions of years, gravity amplified them. Slightly denser regions attracted more matter. More matter increased gravity further. Clouds collapsed. The first stars ignited. Galaxies assembled. Clusters of galaxies emerged. Immense filaments stretched across hundreds of millions of light years, weaving what cosmologists now call the cosmic web. Every spiral galaxy, every elliptical galaxy, every nebula, every planet, every living organism, every human thought can ultimately be traced back to microscopic quantum fluctuations present in the infant universe. This is one of the most astonishing connections in all of science. The largest structures in existence may owe their origins to the tiniest fluctuations permitted by quantum fields. And yet, this realization opens an even deeper mystery. If quantum fields shaped the entire observable universe, if they determined where galaxies formed, if they governed the birth of stars and ultimately life itself, then we are forced to confront an extraordinary question. Where did those fields come from? Because the Standard Model assumes they exist. General relativity assumes space-time exists. Neither theory explains why the universe possesses these ingredients at all. And that unanswered question takes us to the very frontier of modern physics, where ideas such as cosmic inflation, symmetry breaking, the Higgs field, grand unification, and perhaps even a deeper layer of reality begin to emerge. The deeper physicists explored nature, the more a curious pattern began to emerge. Every great breakthrough in physics seemed to remove one layer of mystery, only to reveal an even larger one beneath it. Newton explained why planets move. Einstein explained why gravity exists. Quantum mechanics explained why atoms remain stable. Quantum field theory explained why particles behave the way they do. But each answer quietly replaced an old question with a new one. If particles are merely excitations of quantum fields, where do the properties of those particles come from? Why does an electron always possess exactly the same electric charge? Why do photons always travel at the speed of light? Why do quarks interact through the strong nuclear force while electrons completely ignore it? Why are there exactly 4 known fundamental interactions and not 5, or 10, or infinitely many? These questions all point toward an idea that sits at the heart of modern physics: symmetry. To most people, symmetry means beauty. A butterfly's wings, a perfectly cut diamond, the petals of a flower. But to a physicist, symmetry means something far deeper. It means that nature behaves the same way even after certain transformations. Imagine standing alone in deep intergalactic space. No nearby stars, no galaxies visible, only darkness stretching for millions of light years. Now imagine performing an experiment,
perhaps measuring how an electron moves inside a magnetic field. Tomorrow, you repeat the exact same experiment. Nothing changes. Nature does not care whether the experiment is performed today or tomorrow. This simple fact is a symmetry. Now imagine traveling 10 billion light-years away to another galaxy. You repeat the experiment again. The result is identical. Physics does not appear to care where you are. Another symmetry. Turn your laboratory around, rotate it by 90 degrees. The laws remain unchanged. Another symmetry. These ideas may seem almost trivial, yet Emmy Noether, one of history's greatest mathematicians, discovered something astonishing in 1915. Every continuous symmetry in nature corresponds to a conservation law. This is now called Noether's theorem, and many physicists consider it one of the deepest mathematical insights ever discovered. Because time behaves symmetrically, energy is conserved. Because space behaves symmetrically, momentum is conserved. Because rotating a system changes nothing, angular momentum is conserved. Conservation laws are not arbitrary rules. They arise naturally because the universe possesses deep symmetries. The implications are extraordinary. The stability of stars, the motion of galaxies, the orbits of planets, the operation of every electrical circuit all ultimately trace back to symmetries woven into reality itself. But quantum fields reveal something even stranger. Some symmetries are hidden. Imagine a perfectly round pencil balanced vertically on its sharpened tip. From above, every direction looks identical. The system possesses complete rotational symmetry. Now imagine the pencil begins falling. It must choose one direction: north, south, east, west. The laws governing the pencil were perfectly symmetric. The outcome is not. The symmetry still exists within the equations, yet reality has selected one possibility. Physicists call this spontaneous symmetry breaking. It sounds technical. Its consequences shape the entire universe. Travel back once again to the first tiny fraction of a second after the Big Bang. The universe was immensely hot, so hot that distinctions between several fundamental forces may not yet have existed. Many physicists believe the early universe possessed much higher symmetry than the universe we observe today. As expansion continued, temperature dropped. Just as cooling water freezes into ice, the quantum fields filling space-time underwent dramatic transitions. Certain symmetries broke. The laws themselves did not change. The state of the universe did. These transitions determined nearly everything that followed. Without them, atoms might never have formed. Stars might never have ignited. Chemistry might never have existed. One field in particular became extraordinarily important: the Higgs field. Among all known quantum fields, the Higgs field is unique. Most fields become noticeable only when excited. The electromagnetic field reveals itself through light.
The electron field through electrons. The gluon field through the strong nuclear force. The Higgs field behaves differently. Even in its lowest energy state, it refuses to become zero. Instead, it possesses a constant value everywhere throughout the observable universe. Imagine an invisible ocean filling every corner of spacetime. Not merely surrounding galaxies, not merely filling interstellar space, flowing through planets, through atoms, through your own body. The Higgs field does exactly this. It is everywhere, always. Every particle moving through space is also moving through the Higgs field. Some interact strongly with it, others barely interact at all. This interaction determines one of the most familiar properties in physics: mass. Popular explanations often say that the Higgs field gives particles mass. While useful, that statement deserves refinement. Mass is not handed out like prizes.
Instead, different particles couple to the Higgs field with different strengths. Imagine two people walking across different surfaces. One crosses polished ice. The other struggles through waist-deep water. Both are equally determined, yet one moves effortlessly while the other progresses slowly. The difference lies in how they interact with the medium. Particles behave similarly. Electrons interact modestly with the Higgs field. Top quarks interact extraordinarily strongly. Photons do not interact with it at all. This is why photons remain massless and always travel at light speed. The discovery of the Higgs boson in 2012 at CERN represented one of humanity's greatest scientific achievements. But notice something subtle. Physicists discovered the Higgs boson, not the Higgs field itself. The boson is simply a ripple. Once again, the field comes first, the particle comes second. Exactly the same story repeats itself, again and again and again. Every time physicists think they have reached a fundamental particle, they instead discover another quantum field. This repeating pattern naturally leads to an uncomfortable question. Could quantum fields themselves also be excitations of something even deeper? Modern physics does not yet know. Before we reach that frontier, however, we must understand another remarkable feature of quantum fields. They do not exist independently. They constantly interact. Picture the Milky Way, roughly 100 billion stars, each orbiting the galactic center, each possessing its own planets, magnetic fields, stellar winds, radiation, and gravity. Yet none exists in complete isolation. Every star subtly influences every other through gravity. The galaxy behaves as one enormous interconnected system. Quantum fields display an even richer web of relationships. The electron field interacts continuously with the electromagnetic field. Quark fields interact through gluon fields. Neutrinos interact through the weak nuclear field. The Higgs field influences nearly every massive particle. Reality resembles less a collection of independent objects and more an immense cosmic conversation, each field constantly responding to all the others. This picture extends far beyond atoms. Inside the heart of every star, quantum fields govern nuclear fusion. Protons approach each other despite enormous electrical repulsion. Quantum tunneling, another consequence of quantum mechanics, allows fusion to occur. Without tunneling, the sun could not shine. The heavier elements making up your bones, your blood, and your brain would never have formed. Every carbon atom inside your body was forged because quantum fields behaved exactly as they do. Later, when massive stars exploded as supernovae, heavier elements such as gold, uranium, and iodine formed under extraordinary conditions. Those explosions scattered their newly created atoms across interstellar space. Billions of years later, some became planets. Some became oceans. Some eventually became living organisms capable of asking where those atoms came from. The story of quantum fields therefore doesn't remain confined to microscopic laboratories. It stretches across cosmic history. From the first trillionth of a second, to the birth of galaxies, to the formation of Earth, to consciousness itself. And nowhere is this connection between the quantum and the cosmic more dramatic than in black holes. At first glance, black holes seem governed entirely by Einstein's general relativity. Gravity compresses matter until space-time curves so intensely that nothing, not even light, can escape. Yet the moment quantum fields are introduced near an event horizon, something astonishing happens. In 1974, Stephen Hawking made one of the most surprising discoveries in theoretical physics. Black holes should not be completely black. Quantum fields near the event horizon predict that black holes slowly emit thermal radiation. Today, we call this Hawking radiation. Contrary to many popular descriptions, this phenomenon is not simply particles magically reappearing from nothing. Rather, it emerges from the behavior of quantum fields in highly curved spacetime. gravity changes what different observers consider a vacuum. The result is that distant observers detect radiation escaping from the vicinity of the black hole. If Hawking's calculations are correct, every black hole slowly loses energy. Over unimaginably long timescales, even supermassive black holes containing billions of solar masses would eventually evaporate. Think about the enormity of that statement. Objects once believed to consume everything forever may themselves slowly disappear because quantum fields refuse to remain perfectly silent. It is another reminder that fields, not particles, appear to be the deeper language through which nature operates. And yet every answer continues opening another question. If quantum fields shape atoms, stars, galaxies, black holes,
And perhaps the evolution of the universe itself. What determined the existence of those fields before the first stars ever shone? Or were they present from the very beginning? Or could they themselves have emerged from something even more fundamental?